Another idea that's central to quantum theory and that comes out of wave-particle duality is the Heisenberg uncertainty principle, first proposed by the German physicist Werner Heisenberg in 1927. And the Heisenberg uncertainty principle comes out of the recognition of how we actually observe anything. We observe objects by bouncing photons of energy off of them and having them come back to us. We did this when we talked about radar ranging, how we bounce radio waves off planets and asteroids and measure the time it takes for them to come back to us. But in order to bounce an electromagnetic wave off of an object, the object has to be much larger, or at least larger than the wavelength. We saw that, we talked about that with the electron microscope, that viruses are much smaller than the wavelengths of visible light, and so the visible light waves don't bounce off them. Well, when you get down to the subatomic world, objects there in the quantum realm are so tiny that not only do we have to use short wavelength waves, but those waves, remember, the shorter the wavelength, the more energy that wave has. And when those waves hit such a tiny little particle, they're actually going to affect the particle and they're going to change that particle that we're trying to measure. For example, the first change will be that the wave, the electron wave, for example, will collapse down to a particle. That means that when we're trying to determine a property and we're measuring it by bouncing photons or waves, electromagnetic radiation off of those tiny little particles, we actually affect the particle itself and we change some other properties. So, for example, if we want to know where an electron is and we bounce a wave off it, then we might know where that electron is, or at least where it was, but now the energy has actually sped the electron up, which means we know less about how fast that electron is moving. So let me illustrate this. When we're using radar ranging, we bounce wavelengths of electromagnetic radiation off, say, an asteroid, and it hits it and comes back to us, and we measure the time. But if you are trying to measure something like an electron, and I've tried to depict it here as a cloud, as a waveform, then you can't use visible light. The wavelengths are just too long to actually bounce off the electron. You have to use a much shorter wavelength of EMR. But remember, the shorter the wavelength, the greater the energy of that wave. And so when this quantum of energy hits the electron, it's actually going to affect it quite significantly. So here we could know that the electron was over here, but now we've actually moved it and we've actually increased its speed. So if we wanted to know its speed, we would be much less certain because we don't know the original speed, and now we also don't know how much speed we added to it by observing it. So what this tells us is that at the quantum level, properties of matter and of particles actually blur together in a way that if you try to measure one, the more certainly you try to pin one down, the more blurred out another property becomes. To give you a little completely unrealistic analogy, but imagine that you wanted to know your mark in chemistry and physics, and you had the same teacher for both. And so you asked, well, what's my chemistry mark? And your teacher looked it up in the computer and said, oh, I see here it's 84%. Okay, what's my physics mark? So your teacher looks and opens up the mark folder for that and finds, you know what, I can't open it up. I don't know. I know nothing about your physics mark and I can't remember anything. Come back tomorrow. So you come back tomorrow and your teacher looks in, and now instead of having a very precise numeric grade, all your teacher can tell you is that you have an A. This is less precise because it's somewhere from 80 to 89. Rather than exactly 84. So they check your physics mark, and now they actually know something about your physics mark, but not very much. They can tell you, well, it's over 40%. The next time you ask, your teacher is much more vague about your chemistry mark. Well, I know you're passing, but I can't tell you anything more. And then you ask about physics and they say, okay, well, I know you're passing that as well. If you know that your mark in chemistry is over 40%, you're very, very imprecise in the chemistry mark, then you can be more precise in the physics mark. And if you know nothing about the chemistry mark, then you can know your physics mark exactly. Now, this, of course, is not the way things work on our scale, but according to quantum theory and the Heisenberg uncertainty principle, this is the way the universe works when you look at it on the smallest scales. So at the quantum level, there really is this blurring of properties. It's not just a problem with observation, it's the way the universe really works. And that imprecision, the limit, the lower limit on how precisely you can know something, is actually linked to Planck's constant. So here, for example, if you know the location of an electron very precisely, then you know its momentum or its speed very, very imprecisely in a way to maintain this factor of Planck's constant over 4 pi squared, over 4 pi. And again, the more you know about one, the less you can know about the other in order to keep this relationship the same. This is sort of like, if you remember, space and time, length contraction and time dilation, and they change by certain amounts to always keep the speed of light constant. In this case, the universe works in such a way that position actually blurs out the more precise momentum becomes, and vice versa, all to keep this factor steady. Okay, so this uncertainty is linked here to Planck's constant. In this video, you'll see a little demonstration that actually shows you the reality of Heisenberg's uncertainty principle, that it's not just a matter of measurement. It actually happens that as the position of a particle is narrowed down, its momentum will become more and more spread out, and vice versa.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted, so it could be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. You see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out. Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the uncertainty in the momentum. Now, if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now, h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit, so that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty in momentum needs to go up. I should specify this is uncertainty in momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation. And the more you decrease your uncertainty in position, the more narrow you make that slit, the more the uncertainty in momentum has to go up. And so if these photons are going to the left and the right, that's going to produce a much wider beam. It's really, really non-intuitive, but it's the way the world works.